The next reaction that we're going to look at is the nitration of benzene. So here we're going to take benzene, and I've drawn in one hydrogen explicitly. And if we treat this to nitric acid and sulfuric acid, what we're going to get is nitrobenzene. So pay special attention to the nitro group and the Lewis structure of the nitro group. We have the aromatic ring bonded to nitrogen. That's double bonded to one O, single bonded to the other oxygen. 2 lone pairs here, 3 here. Oxygen has a negative charge, nitrogen has a positive charge. So that would be the nitro structure if you drew it out completely. All right, so take note that it's NO2. Okay, it's not NO. It's not NO3. A lot of people commonly mistake because nitric acid has NO3 and accidentally write NO3 there. It's not NO3, not NO4, NO2. In terms of the mechanism, like the halogenation, there's 2 primary steps. We generate the active electrophile, and then we do the electrophilic aromatic substitution. So to generate the active electrophile, that's going to happen when we mix nitric acid and sulfuric acid. So what I'm going to do is draw out the structure of nitric acid. So it looks like this. And then the sulfuric acid is going to be a proton donor. I'm going to draw it somewhat abbreviated. Under these conditions, when you have nitric acid and sulfuric acid, the sulfuric acid is acting as your acid and donating the proton. Nitric acid is acting as a base here because sulfuric acid is more acidic. So what we're going to do is use a lone pair on this OH, and we're going to protonate it. So I'm going to draw an arrow to the proton in sulfuric acid, and then we'll lose the conjugate base, hydrogen sulfate. So what we get here is protonated nitric acid. So it looks like that. And the conjugate base. So now what you should spot here is water attached. And anytime water is attached to something, it's going to be a really good leaving group that we're going to lose. So what happens next is these electrons on this oxygen on the left come down to form a double bond, and then you lose water. So we lose water, and we get O, double bond N, double bond O, and there's still a positive charge on the nitrogen. And this species is highly electrophilic. This is known as the nitronium ion. And that's our active electrophile. Now that we have our active electrophile, we can react that with benzene. So here's benzene. I'm going to draw in a hydrogen for emphasis. We'll react that with this NO2 plus, and I'm going to abbreviate it like this. We're going to use a pi bond in benzene and attack that electrophile. From there, now I'm going to put the NO2 on the same carbon where I've drawn in the hydrogen. And then the other carbon that was part of the pi bond will bear the positive charge. So we're not quite done because we've broken aromaticity temporarily. But for this last step to regain the aromatic ring, you can be generic and use B. You could use, we have water floating around that can act as a base, or you can use the hydrogen sulfate. Let's just use that as our base to take this proton. Those electrons will come back down and give us the aromatic ring. So that's how we get the nitro group onto the ring. If you want to draw the byproduct here, all we've done is regenerated our acid.